C equals 2 pi over omega, yes.
Omega.
Yep, where omega is your frequency.
So then pi is similar to root 10.
Yes.
It's asking for M3, is the problem?
Yeah, so the problem is asking for M3. So, now that we have our mode shape, we have our omega, we have our M inverse K, take a wild guess as to what we're going to do next.
You're multiplying.
We're going to do the eigenvalue problem, that's right. So, what that's going to look like is you're going to have M inverse K minus lambda I, where lambda is equal to omega squared, times x equals 0. And so, this is known, that's known, therefore we can solve for the unknowns inside M inverse K. So I'm going to go ahead and write that out. I've got 2, 0.1, 2, and 1 right here. This is all equal to 0. This is now going to be minus lambda, which is going to be omega squared. We know that omega squared is equal to 10. So we're going to have minus 10, minus 10, minus 10, minus 10. Okay, so a 4x4 matrix is kind of daunting,
It is.
right? The good thing about this one is there's a secret about this problem that's going to make it way easier than solving a 4x4 matrix. Can anybody take a stab at what that's going to be? If we're
Well-
solving for M3.
Yeah, but M3s are only on row 3, so you probably might have to expand that one.
Just solve for the third row.
Yeah. So we've got one unknown, 4 equations, which means we only need one equation to solve it. And so that's what we're going to do. Your sharp eye said that we only need to pick this third equation.
You figured that out on the exam?
Yes.
Wow.
I mean, you're going to have to do the same thing. That's just a property of systems.
So he's probably gonna do something like that, right?
Yeah.
He's gonna give us a big matrix and then.
Actually, yeah. Like somebody sent me a email saying, "Could you solve a problem similar to this?" And I was like, "Oh yeah, I know exactly how to do that." So yeah, you're gonna be expected to see that. Like, okay, sorry, let me backtrack. A property of linear systems, so things you can represent with matrices like these, is whether it's solvable or not. And what determines a linear system to be solvable is that your number of unknowns is less than your number of equations. So for example, when you're doing like incompressible flow in fluids or aerodynamics, we had 3 unknowns. We had velocity, we had pressure. That was actually 2 unknowns. And then we made 2 equations, so they were solvable. This one, 4 equations, 1 unknown. This one is redundant, actually. So we only need the 1 equation to solve that. So I'm going to write that actually. Linear systems. Systems solvable criterion, which is number of unknowns is less than or equal to the number of equations. This is a good thing to know just for the rest of your life. Like, my statics professor taught me this a long time ago, and I was like, oh really? I had no idea. Like, this is just a good thing to know. So, if it's less than or equal to, that means the minimum number of equations is just the number of unknowns you have. Therefore, that's why we can justify only using this equation. So now what we're going to do is we're going to matrix multiply only this third row, which is going to be 0 times 2 plus 0.1 times 1600 over M3 plus 2 times 20 over M3 minus 10 plus 1 times 0 equals 0. These items are going to cancel to 0. Then we're left with 160 over m3 plus 40 over m3 minus 20 is equal to 0. Now what we're going to do is, this is a simple algebra problem, which is we have 200 over m3 is equal to 20. We're going to multiply both sides by m3 and then divide both sides by m20. Therefore, that's what this means. Have you all seen this before? Yep, therefore m3 is equal to 200 over 20, and m3 is simply equal to 10. And that's how we solve that problem.
That was it, just to calculate M3?
Yep.
So if you're not given, it gave you omega in the problem statement. But if you don't, you're not given it, you just use the period, so like period equals 2 pi over omega.
Yep.
What if the periods are different for each?
They won't
They
be.
wouldn't happen because they'd be the
So what
same system,
happens
so.
is for linear systems, you don't have different frequencies for each mass. You have the same frequency for the entire system, and the mode shape tells you how much each mass responds. So you're always going to have the same frequency for each of the masses in a linear system like this. And so the key to this one was realizing that A, you had all the information you need. B, your eigenvalue was going to be omega squared. C, you only needed this one line to be multiplied instead of solving a 4x4 system.
So in terms of our main equation here,
Yeah.
like that x is the
mode shape.
eigenvector as well. Like,
Yes.
that's
The mode
the
shape and the
equivalent?
eigenvector are the exact same
Okay,
thing.
that's what I thought. And then we multiplied that by inverse k.
Yep.
We didn't do anything with the lambda.
We did. You see how I have 1 minus 10, 10 minus 10, 20 over
Oh.
m3 minus 10,
I missed
25
that.
minus 10?
Yeah.
Omega squared equals 10. And so
I see.
lambda is omega squared, therefore, and it's only on diagonal elements. Therefore, this matrix I change from just m inverse k
I see.
into m inverse k minus lambda identity. Therefore, this is what solves the eigenvalue problem, not m inverse k times x equals 0.
I see.
So you have to factor this in because that's crucial. That gives you this minus
I got
10
you.
right here, this minus 20,
Yeah.
because without this, m3 would be equal to 0.
I see. And it'll always only be on, or it'll always only be on the diagonal, right?
Yes, that's why you have this I right here.
Right. Okay. Cool.
I remember in exam 1, he gave us a graph with like, instead of time, I think it was distance or something. Does anybody have their exam 1?
Not on me.
Yeah.
So what's good about this one is, since you're already having to deal with like things that are much more complicated than just a one mass system, you're not going to have to worry about damping, you're not going to have to worry about like too many tricks like that. Okay, so are we good with this one?
It's pretty straightforward.
So it's just recognizing all of the elements in the eigenvalue problem. Okay. So now we're going to move on to more of a conceptual question. And then, because it's conceptual, I'm going to make it open-ended at first. I'm not going to immediately solve it myself. I'll get some ideas from y'all, and then I will shoot them down if they're unsatisfactory. And then, is this upside down? Oh. Weird. Okay. All right.
I know he's gonna play a video, right?
Yes. Okay. So that's actually what's going to happen next. He's going to play that video, right? And what you're going to see is 3 masses like this, probably.
I feel like you're gonna give us something super complicated.
Nah.
Jumping all over the place.
And you're going to see them moving up and down.
Oh, up and down.
Well, not left to right.
See, that's what I was
He would-
scared of.
he would do something
That is
like that.
different.
That is different. I feel like they're all.
Like,
He's gonna do one where you're gonna have to circle all the options.
Yeah, it's gonna be 0 out of 7 of them.
So what's gonna happen is you're gonna see one that starts moving up, these start moving down, and there's gonna be some differences in amplitudes. What you're recognizing from that movie is that you can determine the mode shape from that movie. So what that mode shape does is it's gonna be all of your relative amplitudes. For each mass, and in parentheses I'm going to put degree of freedom. So you're going to watch that movie and you're going to be asked to be given a mode shape, and then quite literally on the exam you're just going to see X, movie, and then some empty brackets. That's what you're going to see for that problem, and you're going to be asked to put in some numbers. So what you're going to see is one of those numbers is going to be equal to 1, and what you need to recognize from the movie is you're just going to write the amplitudes of each of the vibrations. It's going to be on a graph like this, where you're going to have like you're going to have something like this. And so all you're going to do is just follow it with your eyes and then write the amplitudes for each of the masses. And then if this one's moving up while this one's moving down, just go ahead and assign this one to be positive, and then just say that this one's negative and that this one's negative as well, if they're moving in the opposite directions. But if they're moving together like this, then they're the same direction. So in this case, because I have this one going up while these are going down, this would be like a positive 1, this would be like a negative 0.5, and this one would be like a positive like 4 or something.
and it's not gonna be super like complex where it's like
No,
mass one moves and this one all of a sudden like
there wouldn't be a phase, no.
phase shift yet.
Even if there was a phase, if the mode shape doesn't include the phase, so it's just going to be the amplitudes that you have to look at.
Okay.
Does that make sense?
Phase
Yeah.
shift.
You're just looking at all the amplitudes for the masses, noticing whether there's a phase or not. Like if there's like opposite directions of movement, you write negatives to talk about that, and then you're good to go. So literally all you have to do is just write 3 constants. It's the amplitudes and then whether they're positive or negative. You good with that?
It's a 20
Is there an expected like logic to it we should all like is it something like if one person defaults to say, let's say we go with the smallest one as 1, and then we have like a positive 2 and a 3, and then someone arbitrarily decides they want to have the biggest one be 1 and then have fractions for theirs?
The property of eigenvectors means that all of those are valid answers.
It's just
So it doesn't matter as long as one of them is 1.
Okay.
One
But-
of them has to be 1.
Yes.
I was about to say, is that the sole qualifier, and then however we decide to interpret it is there
It's,
isn't like an expected form he'll want.
It's just
us
like
to
mixed
default to
numbers.
for standardization.
it's just like when you're doing mixed numbers and fractions or improper fractions. Like an improper fraction is like one where you take 3 over like 3 amplitudes that are bigger than 1. But when you reduce that down to the smallest equivalent fraction, that's like a normalized eigenvector. They're both the same
Yeah.
decimal, but there's 2 different balances of numbers.
Yeah.
The ratio is the same, but they're 2 different forms. As long as you present the same as long as it's an equivalent eigenvector, you're gonna be okay.
Okay.
So you can choose any of those to be 1, but most likely the amplitudes of one of those is literally going to be 1.
Okay.
I thought in class he said it didn't have to be the case.
Well, like ambient and you have like fractions.
I thought that as long as it was scaled properly, it was fine.
Yeah.
Exactly.
That's what I'm saying, is like,
It doesn't
Yeah.
matter.
There's
if it's
no-
scaled
yeah.
properly, you're okay.
There's no him
but
going tisk, should have formatted it, whatever.
Like,
Okay.
instead of-
X3 should have been 1! There's gonna be none of that.
Okay.
So just, as long as the ratios between each of the, like, masses is okay, you're gonna be fine. Okay. Alright. And the last two conceptual problems.
And we pretty much have, we know one of the questions, the movie question.
Yeah, that's not one of them. There's two more conceptual problems. There's like, that was number 3. There's like a 4A and a 4B. Okay.